3D etc. element, 3D elements, brick element, tet element, and pyramid elements. Okay, so yeah. So we also discussed about 1D elements. Let us start with today's session. So basic 1D, just I want to touch base again. 1D elements are line elements. We have both linear and quadratic. Similarly, we have 2D elements. 2D elements will have are generally area elements, which have like linear and quadratic. Typical shapes will be tria as well as quad. So we have 3D elements. We have various types of shapes available in 3D elements. Most versatile will be brick element and tet element, and also we also have linear and quadratic. Apart from tet and brick, we also have pyramid elements, and we discussed about modeling strategy when you try to do hybrid mesh with both the brick and tet mesh. So we discussed, and also we discussed about shell modeling. Just I want to give more emphasis on shell modeling. Typically, shell modeling, both shell modeling and plane elements, both will use area elements only. The important thing, difference between shell elements and plane elements are, plane elements can be used only for plane areas which are on or in plane. Okay, so that means the complete cross section or complete area should be in one plane, so it should not have any curvature. Okay, whereas shell elements are used both in both areas which are in plane or out of plane. Okay. Generally, these shell modeling approach can be used only when the length to thickness or radius to thickness is more than 5. So this is some component. So here to have a shell modeling, first we need to extract mid surface. The mid surface is nothing. That surface we need to extract. Then that will form as an area, and then we'll mesh with the area elements. Yeah, shell mesh describes the shell, and the finite element solution represents the deformation of the middle surface. Okay, so even though we have 3D geometry, we represent mid surface. So when you try to solve finite element modeling with shell elements, the deflections or results will vary across the thickness. Even though we represented shell elements at the mid surface, we assign thickness of the component. Okay. So even though we have meshed with the shell elements in the mid surface, but the finite element solution will give for both middle surface, top surface, and bottom surface. Okay. So basically, the stresses and deflections will vary across the thickness. So yeah, shell elements allowed to calculate membrane bending in plane transfer shear stresses. So it will do all those things, like it will calculate membrane stress, bending shear stress. So typically these shell elements are used for thin panels and just made with sheet metals. So for example, if you see car automobile bodies, most of the things are formed by sheet metals. So those things we can model using shell elements. So one of the question arises why can't sheet metal use 3D elements? Okay, why we need to go for shell modeling? So one of the important thing is uh, when you try to mesh with the solid elements, we can mesh with solid elements, but it is very important for us to make thick elements when you try to mesh a model. When you try to mesh a model very thin, when you try to put elements 2 or 3 elements. Okay. Well, if it is a very thin sheet, then our element thickness is very small here compared to here. So that will affect the aspect ratio of the geometry. Okay, element aspect ratio. It will affect the element aspect ratio. So, and we also have various issues because the behavior may not be appropriate because of very thin sheet. So for that purpose, these shell elements are derived so that we can get a minimum with a great accuracy of the results. So one other thing is we cannot put too many elements across the thickness. Okay. Whereas if you model a shell element, it is very simple. We can model one area. We can extract the mid surface and we can model this area and we can put a element and we can assign these elements. So that will represent this component. So one of the important thing is it will reduce the problem size and it will give the results. It will give results with greater accuracy. Yeah, more on shell elements. This shell element is a collapsed of solid element. Okay, so when you try to call shell element, okay. So now what will happen is these four corners. This corner represented by this length because we are assigning thickness. Okay, this corner represents this part, and this corner represents this, and this corner represents this part. Okay, so that is shown here. Okay, this IM represents this I, and JN represents by J, KO represents by K, and PL represents by L. So that sides of the solid element denoted by IM, JN, KO, LP are collapsed. Each edge is now represented by one node. So a solid element has a 3 translation degree of freedom, whereas shell elements have this solid element will be having 3 degrees of freedom, that is X, Y, Z. Whereas shell element has 6 degrees of freedom, that is X, Y, Z, and rot X, rot Y, rot Z. To take this one node, it will have X, Y, rot X, rot Z. Okay, so it will have 6 degrees of freedom x, y, z and 3 rotations. Whereas for solid elements, it is having only x, y, z. Three translations. Three translations here. Here, three translations and three rotations. Shell element is having three translations, three rotations, and solid element is having three translations. So one of the reason why shell element is having 6 degrees of freedom, why not 3? The simple reason is the shell element, the edge is shell elements, the edge is represented by one node. Okay, this edge represented by one node. So to capture the edge behavior, we need to have that additional degrees of freedom, 3 additional degrees of freedom. So we'll see why that is required. So same thing what I explained here, same thing is graphically represented here. Shell element have 6 degrees of freedom, translations and 3 rotations. Same thing is represented here. If I take node, this is the translation along y direction, translation along z direction. Okay. So and we also have rotations along x direction, rotation along y direction, and rotation along z direction. So this is for shell elements. Okay. Same thing if you take a solid element, so it will have only 3 degrees of freedom. That is translation in x, translation in y, and translation in z. So this is the basic difference between shell element and solid element. So coming more on understanding about shell element, if you see that edge ij, this is the shell element. This bold area represents shell elements. So edge ij is represents phase 1 to 5, 6. This phase is represented by ij. Similarly, jk is represented by 2, 3, 6, 7. So these phases are represented by line. So when the bottom 1 2 of phase 1 2 5 6 1 2 this bottom edge, this 1 2 5 6 phase, this bottom 1 2 is more relative to the top 5 6, then there will be a rotation. Okay, so what does it mean is like one, two, five. Okay, when this 5 6 edge moves relative to 1 2, so that means if it is moving relative to 1 2, then there will be a rotation will be there. Okay, so that is called rotation degrees of freedom. Similarly, bottom 2 3 of the phase, similarly bottom 2 3 of 2 3 5 6 moves this bottom edge 2 3 moves relative to 6 7, then there will be again some rotation will be there. Okay, so these are the two out of plane rotations at the node 2 or node j. So one rotation, node j here. So node j, there will be one rotation here. Okay, about this space. So there will be one rotation here, and there will be one rotation here. Okay. So there will be two rotations at J node. One with respect to 1 2, one with respect to 2 3. So these are the two rotations. There will be third rotation will be there, that we generally call in plane rotation. What does it mean is, like in general, out of plane rotations of nodes of a shell can be defined in two orthogonal components in the same plane. In case of node J, an out of plane rotation can be defined by rotation about Ij, and another rotation about orthogonal of Ij. So there are two rotations. If you take one jth node, there will be one rotation along the about the edge Ij. There is another rotation along the Jk. The additional degrees of freedom is an in-plane degrees of freedom, is also known as drilling degrees of freedom. So apart from this these rotations about Ij and Jk, there is a rotation normal to these two planes Ij and K, that is normal to this one, that is called as in-plane rotation or drilling degrees of freedom. So these things basically this related to rotation are required for shell elements, so that it will be represented by so that results can be calculated at top and bottom fiber. So just one simple example, what we can demonstrate is, suppose program calculates some deflection here, U. Okay, this is mid, and we have bottom, we have top. So when component is subjected to bending, so the component will bend like this. Okay. So when component is subjected to bending load, so it will be like this. So here program will calculate at the mid, but it has to interpolate at the top and bottom. So how it will interpolate? It will we also have rotation. Okay. So this information is given to program h or thickness, and this element has additional degrees of freedom rotations. These rotations and translations at the mid surface will use rotations and the thickness. These three things will get the results at the top and bottom surface. This is simple math. Okay. This into height will give this value, as you know, as you are aware. Okay. So that is the main advantage of shell elements. If you can calculate, first of all, our problem size will be reduced. Then it will also calculate bottom and top surface stresses along with mid surface. So in general, for an element, if it is having degrees of freedom, so that degrees of freedom will be in turn represented into as force. Okay. For translational degrees of freedom, generally we will be having a force. For rotational degrees of freedom, we will be having a moment. So this is a typical shell element. So for one shell element, it will have, if it is quad, it will have 24 degrees of freedom. So each node will have 6 degrees of freedom. So if you want to solve a problem with shell element, one shell element with quad shape will have 24 degrees of freedom. So this is a 3 node element, and this is 6 node data. This is 4 node, and this is 8 node quad. Let us closely look into some simple example. Let us take a cantilever subjected to point load. So it is having a 200 length and thickness 2 Remember the thickness to length, length to thickness should be graded is we are having 100. The ratio is length to thickness is 100. So it is meeting that here, and so we modeled a plane area, and we meshed with shell elements. We have assigned thickness 2 and we have used this Young's modulus and Poisson's ratio. This is the width of the plate, 10 So when we try to solve this problem, we got maximum deflection of 20.87, and we also got maximum stress of 368 S1 principal stress. Okay, so this is the maximum deflection. It is happening at free end, and maximum stress is happening at the fixed end. Now this is subjected to pure bending. Okay, what is meant by pure bending? Pure bending is it won't subjected to any membrane stresses. That means if you see this stress distribution cross section in pure bending, the top fiber will be in tension or compression, and bottom fiber will be quite opposite. Okay, the magnitude should be remain same. Then we will call it as a pure bending. Okay, so here we are subjected to a complete pure bending load, so resulting into complete pure, like top and bottom are subjected to same stress magnitude. So now we try to extract stresses with the top and bottom fiber. Okay, if you see the top fiber, okay, we extracted Sx along directional stress along the length, and we got 368 tensile stress. Okay, if you see here, it says Sx in top fiber. Okay, similarly for Sx at fiber, we got perfectly reversed compressive stress 368.733. This is completely pure bending. And there is no stress at all. Okay, this is the example of pure bending. So this is how we can extract results in shell elements. We can extract stresses in mid surface, top surface, and bottom surface. So these stresses are calculated based on the rotations, based on the additional rotation degrees of freedom available in the shell element. Translation. Rotation. Because we have rotations in the shell elements, it is allowing us, it is helping us bottom and top fiber. So any questions? This is very important, shell elements. It is very easy to model shell elements, but it is very tough to understand the theory behind it. So if you have any questions, just let us know. Let me know. Remember the basic equation of motion. F equals to A. So U is nothing but displacement. Okay. So here U, it is having a displacement vector. Okay. In displacement matrix, we will be having Ux, Uy, Uz. Or you can put rod X, rod Y, and rod Z. Okay. So Ux, Uy, Uz, in simple terms, it is a displacement in X and X, Y and Z directions. I hope I cleared your doubt. So any other questions? So if you don't have questions, then I'll continue the session. So we completed shell elements. Now we'll be discussing on solid elements. So there is in-plane and out-of-plane loading. In-plane loading in the sense the loading which is in IJKL. Okay, the loading which we will apply in the plane of IJKL. Okay, that is in-plane loading. Means maybe you can apply load along this plane, along this line or along this line. Whereas out-of-plane loading is where you can apply like pressure load. Okay. Same thing if I take here, when you try to apply load along this along this line, so this loading will remain in plane only. Okay. So when you try to apply load out of plane, means like if I take a typically when you try to apply pressure load on this area, okay, like if I take this one and if I to top view, to try to apply load. This is our plane, and we are applying load out of plane. This is called out of plane loading, and that is called in plane loading. I hope I cleared your doubt. You have to say in plane rotations. So for example, for this node J, the rotations with respect to this line will be having 1. The rotation with respect to this line will have 1, and there is one line. Okay, so about this will be having 1 rotation. So this rotation is 1 degree of freedom. This one is another degree, and this is the 3rd degree of freedom. So this is also called as drilling degrees of freedom. So it is something like this. Okay. So because it doesn't have any phase, it is only 1 point. The complete phase is represented by only complete line is represented by only node J. Node J. Okay. So it will have one rotation coming from ij, one rotation coming from jk, and one rotation coming normal to these two rotations. That is called drilling degrees of freedom. This is a in-plane rotation. Typically, we apply torque for this degree of freedom because for other rotations it is having reference line ij and jk, but whereas for third one it doesn't have any edges. It's only one node here. Hope I cleared your doubt. Loading in top and at bottom directions are also refers. Okay. I hope I cleared your doubt on in-plane rotation and out-of-plane rotation. Now coming to solid 2D. So behavior, say this we already discussed in our model idealization. Just I want to touch base again. So behavior of real structures vary independently along 2 and 3 directions. Suitable assumptions can be made about variation in 2 and 3 directions, 2 or 3 directions. So just to summarize on solid 2D, in model idealization, we can do assumptions. We can do whatever assumptions. One of the important thing is whenever you do assumption, it should not affect physics of the problem. One is physics, it should not affect. Second thing is results should not affect. If you meet both these things, we can do assumptions. So in 2D, in plane 2D problems like axis symmetric, plane stress, and plane strain, there are some assumptions which doesn't affect these two things. It won't affect physics, it won't affect results. So the importance of this thing is it will reduce the computational time, and it is very easy to simulate some of the complex problems. So this is we already discussed about plane stress. Plane stress generally when there are thin components, assume some of the components which are very thin compared to other two dimensions. Like one dimension is very less compared to other two dimensions. Then we can use plane stress assumptions. And one of the important assumptions in plane stress is stress through the thickness. Okay, stress through the thickness. 0. This is the one of the important assumptions. And coming to plane strain, the plane strains are used contrary to plane stress when the length of the member is much larger than the other two strains. Here, the important assumptions is strains are 0 along the normal direction. So along this direction, strains are 0. So these are the two examples, dam subjected to water pressure. This is the dam subjected to water pressure. This can be represented as this one, like a 2D problem, as a 2D problem. Similarly, pipe subjected to vertical pressure. This can be represented as very simple. Okay, no need to model long pipe. And coming to axis symmetry is generally like when if a geometry of the structure, material properties, loads, and boundary conditions are all axis symmetric, then we can do a axis symmetry problem. So one of the important thing is no geometry variation throughout the 360 degrees. Okay, so this should be constant throughout the 360 degrees, and it is described by a rotation of 2D cross section in 360 degrees. So if you try to rotate this cross section about axis, it will form as this volume. Displacement will be in circumferential direction. Loading and deformation are confined to radial and axial direction. So that means there won't be any forces acting on the circumferential direction. Okay. So this is our so there cannot be any force acting along the circumferential direction. If the force can be acted along this direction or this direction. It cannot act. This force cannot be acted along the circumferential direction. Only these two forces we need to consider. If a model is having a force, this axisymmetric problem or the cylinder is subjected to this type of loading, we cannot do any axisymmetric problem. We have to go for 360 degrees model. So some of the examples are like analyzing pressure vessels, pipes, shafts, and aero engine motors. So in general, the 2D model such as plane stress, strain, and axisymmetry will come under 2D solid elements. So this I have prepared this presentation based on ANSYS Classic terminology. In ANSYS Classic, generally the 2D models which comes 2D models such as plane stress, strain, and axisymmetric will come under as a 2D solid elements. So geometry should be in one plane and the loading is in the same plane. So important thing is the loading should be in the same plane and geometry is also should be in the same plane. Typically the plane we refer as XY plane. So let us take a simple cylinder, hollow cylinder. So this is the axis. So in ANSYS, we typically call this axis as Y. So geometry should be aligned such a way that the cross section, the axis should be along Y, and this is the radial direction X. So now this complete area should be in XY plane. You should not have any curvatures. It should be perfect plane. And loading can be applied either you can apply load this direction, radial direction, or axial direction. So you can apply only two directions, either axial or radial. You cannot apply a load which is acting 360 degrees, okay, or on the circumferential load. So in this type of loading, only membrane stress will be developed. No stress variation through thickness. So this is our assumption: no stress variation through thickness. So generally we have 4 noded quads, 8 noded quads, 3 noded triangles, and 6 noded triangles are available. So these are the element shapes available. So generally we need to avoid 3 noded triangles. I'll provide you the details why we need to avoid 3 noded triangles. So elements have mid-side nodes always more accurate because of quadratic nature. We'll get quicker convergence and provide more accurate solution with less number of elements. Elements that have mid-side nodes allow element boundaries to be curved in the undeformed and deformed shape. So important observation from here is the elements having mid-side nodes, it will allow the edges to be curved either in undeformed shape or deformed shape. Like if you see here, in this element, when between two nodes, it is perfect straight line. This is linear, whereas this is undeformed shape. I am telling. Okay, when you when you take a quadratic element between these two nodes, it is allowed to have a curvature. That is because of its formation or quadrature and its formation. So it will allow to have these edges to be curved either in deformed shape or undeformed shape. So that completes two-dimensional. Then coming to one-dimensional. For typical one-dimensional problem, geometry is one-dimensional. So when you take a area elements for area elements, either structure plane stress elements, we will assign thickness. But when you try to model a paint, okay, so this area into thickness will give volume. But in line element, we are modeling only one line. So we need to have a cross section details. What type of cross section? So what are the things we will give is, we will typically give cross sectional area, moment of inertia, and total beam height or details. So these things we will give for beam. For bar and link, we will give cross sectional area only. Beams are geometrically 1D but spatially 2D or 3D. So typically this is 1D, but actually in actual sense it will solve for 3D results. Okay, it will give results in 3-dimensional. Beam elements represents neutral axis of the beam. Similar to shell elements, it will represent neutral axis. Beam elements are used for structures which are longer in one dimension than they are in other 2 dimensions. Okay, so which are longer compared to other 2 dimensions, we go for beam elements. So coming to 1D link elements. Link elements are used to model trusses, sagging cables, links and springs. Link element is a 2-force member, and internal force must be directed along the line that connects two nodes. The member is in uniform tension or compression, so it can take both tension and compression loads. Degrees of freedom will be 3. Translation. Ux, Uy, Uz. So when we have translations, we can apply only force. So you want to apply, we need to have rho x, rho y, and rho z. That way, if we have that, then we can apply moments. For the link elements, we have only translations, no moments. So let us take one example. For 1D link, I applied a simple axial force here, 10,000, and you see the results. It is subjected to 10,000. It is having a cross section area of 240 mm square. Length is 200 mm. These are the material properties details. When we try to calculate, we got a tensile stress of 41 MPa. That is uniform throughout the cross section, and this is the deflection we got it. Overall elongation. So when we try to solve, this is a theoretical calculation. When you try to solve in, we got an axial deflection plot. 0.039683, say it matches with the theoretical value. And here axial stress plot also it is matching with our theoretical value. So when this is a perfect, the load we applied is perfect axial force. When you try to apply bending load, so when I try to apply bending load, it won't generate any stresses when you try to apply bending load, because there are no rotations, okay, rotational degrees of freedom in the 1D link elements, so it won't allow. So when you try to apply two types of loading, one is axial, one is bending, it will generate stresses only axial force. This force will be completely neglected. So that is the reason it is very important for us to understand what type of loading is there in the component and what type of elements can be used to apply the loads. So type of loading is very important to select the modeling approach and element types. So coming to 1D beam elements are used typically either 2 or 3 nodes. First to define center line. So first to define center line, and the third node may be used to define orientation of the principal axis of the cross section. So typically, like we can use third node for the orientation of the principal axis of the cross section. So it has typically 6 degrees of freedom, 3 translations, 3 rotations, similar to shell elements. Whereas in bar element it is only translations. Here we do have rotations. That means we can apply bending load. Okay. Suppose if I have a cantilever, if I ask you to solve the model, what type of element you are in this table? 1D bar element or 1D beam element? Okay, beam or bar. So that means it all depends upon what type of loading it is there. Here we are having this load will cause bending. Definitely we will go for beam elements. So some of the things I'll show you here, but in detail we'll discuss in next session. Coming to solid 3D, so we take brick element, it is recommended. Brick 8 noded is recommended, whereas TET 4 noded is not recommended. Prism 6 noded is not recommended. Pyramid 5 noded is not recommended. Now coming to solids, brick 20 noded is recommended. TET 10 noded is recommended. Prism 15 noded recommended. Pyramid 13 noded recommended. And some typo is here, so same thing, TET 10 noded is also recommended. So similarly for shell elements, quad 4 noded is recommended. Tria 3 noded is not recommended. Quad 8 noded is recommended. Quad 6 noded is also recommended. So similar to well element, solid 2D also, here Tria is not recommended. Tria 3 noded is not, but other things are recommended, like 4 noded quad, 8 noded quad, and 6 noded Tria are recommended. And coming to 1D elements, generally we want, and most of the things whatever we have, they are recommended. We have link 11, link 180, beam 188, beam 189, all are recommended. So this what I'll do, like why they are not recommended, I will give a brief session on that, and then you will try to we can appreciate why they are not recommended. Okay, so this is for your information time being, but going forward sessions I'll update you why they are not recommended. So this completes today's session. If you have any questions, just let me know. So I think you got some 5 sets of materials. So immediately what I will do, I'll send this material through our L&D team. So maybe it will be reached to your coordinators. Then you can take from them all these materials. So any questions, please ask. There are no questions. Okay, thank you very much.